session, we are going to discuss about the concepts of mass defect and binding energy of a nucleus. By the end of this session, you will be able to calculate the binding energy of any nucleus. How is a nucleus formed? Protons and neutrons combine to form a nucleus. If so, the total mass of the protons and neutrons is expected to be equal to the mass of the nucleus formed. But they are not equal. Instead, the nucleus formed has a lesser mass. This shows that some amount of mass has disappeared during the formation of the nucleus. The disappeared mass is termed as the mass defect delta M. Hence, the total mass of the protons and neutrons minus the mass of the nucleus formed gives the mass defect delta M. Let Z be the number of protons, N be the number of neutrons, Mp be the mass of one proton, Mn be the mass of one neutron, and M be the mass of the nucleus formed. Hence, Z into mass of each proton plus N into mass of each neutron minus the mass of the nucleus will be equal to the mass defect delta M. Now, where is this mass gone? The disappeared mass delta M is converted into an equivalent amount of energy to bind the protons and neutrons. This energy that is used to bind the protons and neutrons is termed as the binding energy of the nucleus. Let us now convert the disappeared mass, otherwise called the mass defect, into energy using Einstein's mass energy equivalence. Binding energy is equal to delta M c squared. Hence, when protons and neutrons combine to form a nucleus, some amount of mass is converted into binding energy of the nucleus. The value of binding energy accounts for the stability of the nucleus. If a nucleus has a higher binding energy, then it is said to be more stable. The binding energy of iron nucleus is the highest, and hence iron is the most stable nucleus. Hope you have learnt the concepts of mass defect and binding energy of a nucleus.